So very good afternoon students. So today in this class we will study about transition state theory. So transition state theory. So as the name suggests, it is an alternate approach to the collision theory which is based on kinetic theory of gases. So here we invoke the principle of equilibrium. So let's take an example. So let's say that you have A reactant combining with B reactant to give you products. Now what this transition state theory tells you is that A and B, before they go and form product, they form a complex which is indicated by AB dagger, which then breaks down to give the product. So this AB dagger is called as the activated complex. So sometimes this transition state theory is also referred as activated complex theory. Another alternate name for this is absolute reaction rate theory. So now let's look at some of the postulates or important points about this theory. So the first point is that according to this theory, point number 1, the reacting molecules must form an activated complex before being converted to products. The second point is there exists an equilibrium between the activated complex and the reactants. So these are some of the important premise on which this theory is based on. So let's take an example. So let's say that you have so as I said, so let's take a example. Let's say you have a let's draw the same reactant as we did above. So you have A plus B, which are the reactants. They are in equilibrium with the AB dagger, which is called as the activated complex, or sometimes also referred as transition state. And then this breaks down into products. Now please note that once this transition state or this activated complex is formed, and once it forms products, there is no chance that the products will again come back and form the activated complex. That is ruled out. That's why you see a single arrow from this activated complex to the product. Okay, once products are formed, they won't revert back to this activated complex. So please note that. Okay. Now what is rate? Now what is rate? According to this theory, the rate of the reaction is given by the concentration of the activated complex, into the frequency of decomposition of the activated complex. So the rate depends on two things. One is the amount of activated complex that is formed, the quantity of activated complex formed, and also at what rate this activated complex is decomposing. So both are very important. So we can write this as, in our traditional differential equation, as dA by dt equal to AB dagger into frequency of decomposition of the activated complex. Now we have to determine these two terms that is appearing here. Okay, so we have to determine these two terms. So let me just copy paste here so that things are little nice. Okay, right. Now first let us apply the equilibrium knowledge that we have and derive an expression for AB dagger. So from the above equation, we know that we can write the equilibrium constant for this reaction as K dagger equals AB dagger, concentration of AB dagger divided by A by B. So this is based on this equation 1, if you can call it. Okay, so this is based on equation 1. Okay. Now from this, if you just rearrange, you can get an expression for AB dagger, which is K equilibrium constant A into B. Now the second term, that so we have got this, right? So we have got this. So this we have here. Now we have to worry about the second thing, which is the frequency of decomposition of activated complex. So the second thing that we have to worry about is frequency of decomposition of activated complex. Now how do we go about this? Now let's look at what is happening. Now A is coming and forming a AB dagger. Now you can think of this AB dagger as something like A forming some sort of bond, okay, not a bond in strict terms, but some sort of interaction with B, right? With B, or if you want to take an example, let's take an example like for C double bond O. Okay, let's take a general example which is like A B, okay, some A B is okay, or we can just say something else like yeah, A B combines with C to give you A B to give you A plus BC. So this is a very simple reaction that I think you can understand. So now what is happening here? Here in the, so this is your AB dagger, which is your activated complex, right? So this is your AB dagger, activated complex. Now what is happening here is that one of the bonds here has to vibrate a lot, right? The AB bond, because it has to break, it has to vibrate a lot, and now this AB bond is now converting into a translational motion. Okay, so என்ன நான் சொல்ல வரேன்னா இங்கே வந்து AB bond வந்து vibrate ஆகுது. Okay, right, it can vibrate like this or it can vibrate like this. Okay, அதாவது இந்த ரெண்டு ஏபியும் இப்படி தூரமாக ஏபி இப்படி போகலாம், இல்லைனா ரெண்டு ஏபியும் ரொம்ப பக்கத்தில் வரலாம். So they are vibrating, they are rotating. Okay, but we are concentrating here on vibrational modes. Okay, so they, because for a bond to be broken there should be vibration. Okay, rotational modes and all won't cause rupture of bond, so we are not considering that. So for AB to be broken, இப்போ இந்த பாண்ட் பிரேக் ஆயிடுச்சுன்னா என்ன ஆகும்? இந்த ஏபிக்கு இருக்கிற வைப்ரேஷனல் மோட், the vibrational mode that is there in this AB bond will be converted to a translational mode. Translation mode என்ன அர்த்தம்? Now this AB which was bonded is now able to move freely. A can move separately, B can move separately, right? So one of the vibrational modes, so what is happening here is that one of the vibrational modes is getting converted into a translational mode. So one of the vibrational modes is getting converted to a translational mode, right? So now our task is to identify this vibrational energy. So if we are able to identify this vibrational energy and the frequency of vibration, we can understand what how quickly this activated complex can decompose. So now according to Planck's theory, so we know what is Planck's theory. So according to Planck's theory, this energy of vibration is given by E equal to h mu, where mu is the frequency of the vibration, or we can say that this E vibe is the vibrational energy which causes the rupture of bond, which causes the rupture of the bond, which causes the rupture of the bond. So then according to Planck's theory, we have V vibration equal to h mu. Now according to classical theory, okay, this E vibration energy is also given by, which is the energy that is extracted from the temperature. So this is given as kBT, and so you can equate these two and you can get mu equal to kBT by h, where kBT is the Boltzmann constant. And hence if you substitute this into your equation above, which is this, okay, so let's give this equation some number, let's say this is equation 2. So if you substitute this equation, substituting equation 3 in 2, you get minus dA by dt equal to K dagger A into B by KBT by H. Please note that this H is nothing but Planck's constant. Is Planck's constant. Now, experimentally we also know that this rate is given by K into A into B, where K is the rate constant. So, let us put this as equation 4, let us put this as equation 5. Now, if you compare, since the left hand side of both equation 4 and 5 are same, you can equate the right hand side, and so you get the rate constant multiplied by the product of the reactant is equal to the equilibrium constant of the reaction multiplied by the product into KBT by H. And so you have this A and this A, this B, and this A, this B will cancel with each other, and so you have this K equals K dagger into KBT by H. Now, we all know how this equilibrium constant is related to free energy of a reaction. So, you have this delta G dagger, we will call it as delta G dagger, just so that we know that we are dealing with this equilibrium constant. So, this relationship we all know. And so, we can also write, since delta G is also related to enthalpy and entropy, we can also write this as, now we can rearrange this equation as K dagger equal to exponential minus delta G dagger by RT, or this is equal to exponential minus delta G dagger by RT, can be expressed as, so we will replace this delta G in terms of delta H and T entropy. So, you will get this as minus delta H dagger minus T delta S dagger by RT. So, let me replace this with a square bracket so that we are able to distinguish the two, right. So, this can be written as exponential minus delta H by RT into exponential delta S dagger by RT. Now, this delta H, delta G and delta S are all thermodynamic quantities which we are aware of. So, this stands for free energy, this stands for enthalpy change, and this one stands for entropy change. And please note, they are all at standard condition. Okay, so so you can call them as standard free energy, standard enthalpy change, and standard entropy change. Right. Now we can equate. Now let's compare this expression with the one that we had earlier. Let's compare. Okay, so I forgot to put on equation number, so let me call this as phi a. Now let's compare phi a with 7. Now if you compare phi a with 7, so if you compare phi a with 7, you can replace this k dagger with the rate constant. So you will have k equal to kBT by h into exponential delta S dagger by R. Oh, sorry. So here, sorry, I missed a point here. So here you will not have this t, because this t and this t will get cancelled. Okay, so please note the change. R into exponential minus delta H dagger by RT. So this is the fundamental. So this equation 8 is the fundamental equation for. So this equation 8 is the fundamental equation, or the relationship for the transition state theory. So equation 8 is the fundamental relation of the transition state theory. Now let's compare the results of transition state theory or the activated complex theory on the Arrhenius equation. So we will compare or try to get the relationship between Arrhenius equation and activated complex theory. Now let's go back to the equation which relates the rate constant with the equilibrium constant. So I think according to the above equation, this is equation phi a. So this is equation phi a. So from phi a. Now what we will do is that we want to get this in a form so that it is related to Arrhenius equation. So what we will do, we will just take log on both sides. So if we take log of both sides, you have ln of kb by h into ln of t plus ln of k dagger, or we can say this as, so if you take the differential of this, if you take a differential with respect to dt, so let's call this as, I'll call this as equation 9, I'll call this as equation 9. Now if we differentiate this with respect to t, you will have d of ln of k. So please note, this is the rate constant. By dt equals 1 by t plus d ln of k bar by dt. Now we know what Arrhenius equation is. So according to Arrhenius equation, the rate constant K equals A into exponential minus EA by RT, where EA is the activation energy. Now if you take ln here, so you get K equal to ln of A minus EA by RT. Now again, if you differentiate this with respect to T, you get d of ln K by dt equal to E by RT square. Now let's call this as equation 12. Now if you compare 12, comparing 10 and 12, since the left hand side of both these equation are same, so this is EA, which stands for energy of activation. So I will write it here. So EA is your energy of activation. Now you might have had a question here, like why I am differentiating this with respect to T, because we want to make all these which does not, so these are all constants, right? KB is a constant, so KB is a constant, right? KB is a constant, H is a constant, so this is a constant, Arrhenius parameter is a constant. So we want to eliminate those terms, so that's why we are differentiating with respect to T, right? So now if you compare these equations 10 and 12, you get EA by RT square equals 1 by T plus D of ln K dagger by dt, or we can say EA equals RT plus RT square d ln K dagger by dt. Let me go to the next page. Okay, so let me put this as equation 13. So let me put this as equation 13. So now you have where your now from a thermodynamic relationship known as the want of isochord, we have d ln of K dagger dt equals delta U dagger by RT square, where U is your internal energy change. In many books they use E, but just to make sure that this is different to the energy of activation, so I am using U, where your delta U is the internal energy change, is the internal energy change at constant volume, or you can just say energy change at constant volume, because at constant volume only your internal energy changes, right. So we can write this as EA. So based on, so from equation 13 you can write this EA as RT plus delta H dagger minus delta N RT. So where, okay, so this is your RT square, right. Okay. So what we have done is that if you compare this equation, okay, sorry, so let's say this is 14. So if you compare 14 and 13, we are replacing this value, okay, with this value. So what happens is this RT square, this RT square goes off and you are only left with delta U. So delta U, you know, so the relationship between delta U and delta H. So we know the relationship between delta U and delta H. So you know delta U equal to delta H minus delta N RT. So that's what we are substituting here. Okay. So now from this we have E of energy of activation is equals delta H dagger minus RT delta N minus 1, or we can say delta H dagger equals, or minus delta H dagger equal energy of activation minus RT delta N minus 1. Now if we substitute the value of this, let's call this as equation 15. If we substitute this value into delta H dagger that we got in equation 8, okay, so if we compare equation 8, so now compare, or we can say that substituting equation 15 into equation 8, what we get is that K equals, that is rate constant equals KBT by H exponential delta S dagger by R into exponential minus EA by RT into exponential minus delta N minus, sorry, this should be written as delta n minus 1. Okay, or we can say this as k equals exponential minus delta n minus 1 into kBT by h into exponential delta s dagger by r So you get this expression. Let me just write it little clearly because I am getting confused. So let me just write it a little clearly. So what we are doing here is that we are trying to put this in upfront. So k equal to exponential minus delta n minus 1. So let me put a square bracket here into kBT by h into exponential delta s by r into exponential minus EA by RT. Now we also know that from Arrhenius equation, so let me just give this number. So let's say this is equation 16. Now we know from Arrhenius the equation that k rate constant equal to exponential minus EA by RT. Now if you compare these two equations, you can very well say that the value of A should be this. So this should be the value of A. So we will write it separately below. So A will be equal to exponential minus delta n minus 1 into kBT by h into exponential delta s dagger by r. Now for a unimolecular reaction, we can say that delta, there won't be any change in the number of moles, so delta n will be equal to 0. So this will give you k equals exponential into k T by h into exponential. So this will be exponential 1. Okay, so this is minus and minus will become 1. So this will be exponential raised to the power 1, and you have exponential delta s dagger by r and exponential minus EA by RT. So just a minute. Yeah. Now, if delta n equal to minus 1. So, this will change as k equal to exponential square k into t by h exponential delta s dagger by r exponential minus EA by RT. Okay, so this is the general expression for a rate, not general expressions, this is what your A from Arrhenius equation looks like.